Start. All right. Happy afternoon, almost evening. Couple of notes. I was going through the dates, and then I was looking at, okay, so reading break. Are you guys okay if we have it on the Tuesday? Because then we could do something kind of squirrely for the Thursday. Maybe I post a video or something, and then you can have a little bit longer of a break. Because this is like late in the afternoon, basically Friday. So I'm gonna move it to February 11th, and I highlighted that on our Moodle page. Hopefully that's okay. But there was also a conflict with the Thursday, so I figured may as well just move it for everyone. Okay. I don't have any content on test one because I'm gonna let you guys kind of dictate the pace that we do this at. So we'll get started on chapter 1 today and kind of see how far we get. And so I'll just kind of keep plugging away at it. But if you need me to slow down or possibly speed up, that's fine too. Just let me know. A couple of these things, I rearranged our Moodle page a little bit. I can't remember if I showed you my schedule, but my schedule's here if you're wondering when I might be around, when I would not be around. I did say likely off campus on Mondays because I don't have anything on Mondays, that kind of thing. There's the Zoom classroom link, which I think I showed you last day, right? If you want to hop on Zoom and join online, that's fine during class time, but I use it for all my classes. So if I'm in a different class, then you can join in on that too, I guess. This I know I didn't show you. I put up the link to the Success Center. And so the Success Center, I'll have Kate come in and talk to us. Maybe she hasn't reached out yet, but I don't want to hound her. It's a busy time of year for her. So when she's ready to come see us, then we'll have her come in and introduce herself, and then you'll know who to look for. Okay. And I also posted this great TED Talk, which if you haven't watched it, Angela Duckworth does a lot of kind of research in math education, and so she's this famous researcher, and she does this talk on grit, and it's kind of the main component of learning math. So if you want to get really fired up for the term, then you can watch that, or not, doesn't matter to me. We've got material to do, so otherwise I'd show you the video, but I'm gonna try it because I don't know how the sound would work, so I'm mostly curious about that. So let's see here. Okay. Obviously there's no sound. Anyways, you can watch it. There. You've seen it. It's not so scary. It's just a quick little TED Talk. I knew it. I knew it would be the sound that would bring me down. Anyways, whatever. Like I said, we're going to start in chapter 1 today, and which is just kind of getting used to linear equations. So straight lines, that's it. If I say y equals mx plus b, maybe, right, you can kind of go into the archives and oh, that sounds familiar. And so we'll kind of pick that apart today. And like I said, we'll see how far we get. But there are some kind of core concepts that I definitely want us all to have under control. So even if it feels like a ton of things you already know, that's cool. Just enjoy it. Okay. And what I did is I posted these notes. Now I'll be filling them in as we go, and then I'll post the notes that I've filled in as well on Moodle after class. And so But it's really just so I don't have to write so much. And we'll go through. So this is for chapter 1, and I'll do the same for the rest of the chapters, depending on how well I will eventually, but we'll see how quickly we can get through it. My goal is actually to stretch it out over next week as well, right? Just to make sure that everyone has the same foundation. Okay. But today I'm just kind of gauging where we're at. We're trying to. Difficult. Any questions before we start? Yeah.
The prerequisites for this class. It's not is it Foundations 11 and 12?
You know.
Because I took high school in a different province, and the classes I took would be the equivalents to those. And I'm just wondering if what I've learned in those other 2 classes will be of any use to me in this one.
Principles of Math 11, Pre-Calculus 11, Foundations of Math. Now, I don't really know what any of these mean, so I don't know.
Does anybody know the difference between foundations and applications? Maybe my colleagues not clear.
I think it's all pretty generally the same stuff. Like if you took math in high school, like in grade 11, I think you're set.
Yeah, I think it should be probably any Math 11 is fine.
It's just that in Alberta, the way our classes are set, if you took a math 11, like a math 20-3, you would not, it's not a class in the university would, but if you took like a math 20-2, which I did, now I just don't know if it's Foundations 11 or applications. I learned the quadratic formulas in that class. So
You're good.
Make the assumption that
You're-
it's Foundations.
you're-
Don't remember anything I learned.
Me neither. Probably because it was like 20 years ago, but yeah. All right. So we're going to start off linear equations. Okay. And so it's funny that you mentioned the graphing paper. We will be graphing today, but just sketching, just quick sketches, nothing crazy. And I mean, depending on how deep in math you've gone, right? If you're thinking we're going to do curve sketching or anything crazy like that, we're not going to do that. No. You'd have to go to calculus for that. You're not going to get that here. You're going to do fun stuff. Okay. So I just kind of put these on here. So I reserve the right to move things around as needed. But what have I done? All these things, if you're working on an iPad, for example, they're just from the textbook, right? I'm just snagging stuff from the textbook. So if you've read the textbook, then none of this will be news to you. I'm just going to talk around it, right? Which is how I like to structure courses like these. It's kind of, I'm working in the textbook. If you read the textbook and you work the textbook, then you will do well, okay? Otherwise, it becomes just a ton of information from different sources, and that's cool, and I can give you more, but I want it to be really focused, okay? So we're just gonna slowly work our way through the textbook. I'll talk around it, because they really gloss over some stuff. Sorry, about to sneeze, but it's not coming. So where is it? And where's my sneeze? I'm trying to decide if I want to sneeze or don't want to sneeze. That's my biggest decision. I think I'm leaning I don't want to sneeze, although they're always kind of inverted, but wouldn't it be so too bad if I just Okay. Beginning of the chapter. Where is it? Here. So, chapter 1, linear equations, learning outcomes. We're going to graph a linear equation, and then we're going to find the slope of a line. And then we're going to find the equation of a line, right? Y equals mx plus b. And then we're going to solve some linear systems. Okay. What does that mean? If I have two lines, the point of intersection is the solution of the linear systems. And then we're going to do some application problems, kind of word problems using linear equations. Okay. So if we have a linear equation, usually we start off with some sort of graph like this, right? And so I have an x-axis and I have a y-axis. Okay. And just to help you remember which one is which, because there's only two, you only need to remember one and then you remember the other one, right? And so I had a student one time and she was so cute. She goes, I can never remember which one is the X and which one is the Y. And so she had come up with this scenario where there's a tree and it's falling down on a little guy. And he's down here saying, no. And that's the x-axis. Isn't that so cute? But also very elaborate. So that's why this is the x-axis, I guess. Whatever you need to do. Okay. And so that's kind of the first point I want to make is, okay, whenever we're drawing a graph like this, we have the x-axis and we have the y-axis. Okay. A point in here, let's say a point there, is going to have some coordinate. Now the coordinates are going to have the form of x comma y, right? And so we've got this coordinate for this point, and we could have multiple points, and usually we would use subscripts, and we would say x1, y1, x2, y2, x3, y3, blah, 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 for as many points as we have, right? So hopefully that's all reasonable, right? What's fun about lines is you only need 2 points on the line, and then you can draw the entire line. Okay? And so in order to draw a line, we only need, I was in this classroom last term and I don't remember it being this hard to write, but anyways, it's a me problem. In order to draw a line, we only need 2 points. X1, Y1, that's going to be from point 1. And X2, Y2, give myself a little bit more room. After that, right, if we plot those coordinates, we plot the coordinates. And I know I mentioned it, but I will post these notes after class, right? So just in case you're feeling stressed out, copying it down. Okay, so we plot the coordinates and then we can use a straight edge to connect those dots and then extend the line, and then that's the entire line. Okay. Then we use a straight edge. I'm saying a straight edge. It could be a ruler if you're fancy, but usually we don't have a ruler. So then I just take the bottom of my page and I kind of curl it up and use that as a straight edge. Close enough. Could even let loose and use your calculator edge. Use any straight edge. Right? And then we use a straight edge to connect the points and extend the line. It's always good practice to have more than 2 points, but I usually get lazy pretty quickly and I just end up doing 2 points. Right. So a linear equation doesn't have any powers anywhere, right? No powers on x and no powers on y, right? So just x and y. Okay. Let's see here. Turns out I've got a lot to say. Linear equations. No powers on x nor y. Right? So if there's just an x and a y, then it's going to make a linear equation. So if we look at each of these individually, 2x minus 3y is equal to 6. So I've got just 2 times x, and then I have negative 3 times y is equal to 6. There's no powers on x or y, and so that means it's a linear equation. All right. Same thing here. I have 3x, not 3x squared or 3x to the 3 or 3x to the 4th or anything. When you have that, you have a nonlinear equation, right? And so for us, all our x's and y's are just going to be x's and y's, and that's it, right? And so you can kind of skim through these and make sure, okay, there's just x's and just y's. We're even allowed to have situations where we have no x's, right? So here, this we can rewrite as 2y plus 0 times x is equal to 3, right? The coefficient of x is 0. Yeah.
So when it comes, yeah, when you get equations like that, when it's just 2 something y equals 3, we should turn it into a longer equation?
No, I'm just showing where the x went. So the x is still there, but we don't write it because 0 times anything is going to be 0. And so that's where it kind of disappeared to. It's still technically there, but that's how we kind of got rid of it, right? This one's a little bit sneakier, right? We could rearrange x minus 2 is equal to 0 as x equals 2, right? By adding 2 to both sides. And then I could do the same thing on the y. I could have x plus 0y. Let's see here. I could rewrite this as x equals 2. And then I can take it one step further and say x plus 0y is equal to 2. If you wanted to have x's and y's always, right? But we usually don't write those 0 coefficients, right? Because they don't do anything. Okay. So a line, like we said, is completely determined by 2 points, right? Which is what we said. All we need is 2 points to be able to draw this graph. Okay. And so let's draw or sketch, I should say, these lines that are given. Sketch 2x minus 3y is equal to 6. Just a rough sketch is fine. And like I mentioned before class, if I need you to graph anything on the tests or on the final exam, I'll give you a little grid to use, right? You don't have to think about the grid, but okay. So we said, okay, there's no powers on x and no powers on y. And so then should be a straight line. So all I need is 2 points. How can I find those 2 points? What could I do? I like to set up a little kind of table, and you can pick values maybe of x or of y, and you can plug them in and you can solve for the other value, right? Because these points, right? If I have an x, I can force an x, and then I can solve for what y would be when x is that value, right? So I like to make a table. My go-to move is always to let x be 0, right? That makes my math really easy and almost fun, right? And so here, if I let x be 0, then I have, in general, 2x minus 3y is equal to 6. If I let x be 0, then I get 2 times 0 minus 3y is equal to 6. 2 times 0 is 0. Right? So then I'm left with negative 3y is equal to 6, which means that, what do I have to do? Y, it has to be 6 divided by negative 3. Which must be negative 2. One thing I want to highlight immediately is it's very tempting, even for me, it was tempting to write across, right? But I'm trying to establish good math habits. And one of those habits that I'm going to be really particular about is that you stack your equal signs. Takes up pages. It's funny because I'm working on like a virtual page. It's not a real page. It's not paper. But sometimes I still just want to write across. I get that. And sometimes I will if I'm at the end of a page or something. But in general, you should try to just stack your equal signs. Okay? It's just good practice. Yeah. So what does this mean? This means that in terms of our xy coordinate, when I forced x to be 0, I found that y must be negative 2. Remembering that this is x and this is y. Turns out I need a little bit more room here. Let me just wait. Yeah.
I think I have a question, but when you were isolating the variables, you divided by the same number but opposite sign. That makes sense. So like the 0 minus 3y equals 6. Would you divide the 3 divide each side by positive?
So 2 times 0
Yeah.
is 0,
Yeah.
right? So then I'm kind of ignoring that because then I'm left with 0 minus 3y. Nice. Good. Good. Okay. So x equals 0. I guess I should have pointed it out, but this point here is called the origin and it's at 0, 0. Okay? Not necessarily on the line. In fact, it's not on the line. How do I know that? Because I already know when x is 0, y has to be -2, right? And so this -2 coordinate, let's put it down here. If y, so if this is 0, then of course this is the positive values for y, and this is the negative values for y. And so here I have the point 0, -2. That's a point on my line. Usually what I would encourage you to do is just look at the grid. If I gave you a grid and pick values of x to solve for y that are on the grid, and that'll be easier. I didn't give you a grid in this case, but that's what I would do. Whoa, where did all my stuff go? That's not cool. I definitely wrote a lot of stuff here, but it's not showing up. So that's making me nervous. Let's see here. Add page. Okay. Just keep bumping stuff down. Okay. There. We need 2 points on the line. Pick a convenient. You could do the same thing and let y be 0, right? That might be nice. Where is y 0? If y is here, right, then y equals 0 is on this x-axis. Just to illustrate something kind of spicier, I won't, right? But generally, that's going to be your go-to move is let x be 0, let y be 0, solve for those intercepts, right? But I'm not doing that because that's the next point here. So I'm going to save it, I guess. So if I let x be, I don't know, let's let x be, well, let's start thinking about this. If I asked you to let x be a convenient value of x, right? What would be a convenient value, right? Kind of easy calculations. X equals 3 is nice, right? Why is that nice? Because then you can subtract 2 times 3 from both sides, -3y equals 0, which would put you at the intercept. So it is an excellent, convenient number. But let's do some easy, just pick values that give you easy math, right? Let's let x be 2, just for 3 is probably the best one, but just to illustrate. 2 times 2 minus 3y is equal to 6. Right, same equation. Plugging in x equals 2. When x is 2, what's y? And so now I have 4 minus 3y is equal to 6. I have to subtract 4 from both sides. And so I have -3y is equal to, can I just do 2? We'll see if there's any uproar. Revolt. What did I do? I subtracted 4 from both sides, right? And so here, I'll do it in a lighter blue color. -4, -4. Makes this go away and turns 6 minus 4 into 2.
Make y a fraction.
It does.
Yeah, okay.
That's okay.
How would we break what fractions? though?
You can do it. You can do it. It's harder. It's not as fun. Turns out I picked an inconvenient, convenient value of x. But if you get to this point and you say, well, I don't like that, you can just pick a different value, right? One that you like. Try 3, might be nice. But I'm saving it for the intercepts. So now, let's see here, change this. I get y must be 2 divided by -3. I guess I have enough space. I'll do it as a proper fraction. Not very nice, is it? Can try it. I will say, if you have one of these kind of engineering calculators, they'll give you the exact answer, but you can always ask it for the decimal version, right? And so this fraction is what we call the exact answer. And then y is roughly -0.6667, let's say. It's repeating, but to draw it, it makes it hard. And so this is the approximate answer.
Sorry, will tests ask us about writing down the exact answer versus the approximate answer?
No, I won't be that picky, but it is something I expect you to kind of have a handle on what the exact answer is and what the approximate answer is, right? I'll be pretty picky about using the squiggly equals if you're doing a decimal approximation. I guess I'm committing to you now that I won't take any marks off, but I do appreciate seeing it if you're using a decimal approximation, right? Recognizing that you are rounding, right? Because if you're using this number later on, that will impact later numbers as well, right? Especially when we talk about financial math, right? People get really upset when your rounding loses them $1,000, right? People don't like that for some reason, right? And so we'll see some examples like that, right? Where it's kind of important, right? And so whenever possible, you should use the exact answer. Right? If you have your calculator, a lot of scientific calculators have a store function, right? And so you can store values, the exact values, and you can use them in your calculations later on. And so that's really nice. For graphing though, well, -0.6667 is probably somewhere, let's see here. Y is -1 here, -0.5 here-ish. Let's put negative, I don't know, somewhere like that. We're just sketching it anyways, doesn't matter. This was the value of y when x was 2, which means our coordinate is at 2, and I'm gonna keep it exact, and 2 over -3. Or what happens to that negative? Usually we float it up top so we don't miss it, right? But it can only be in one of those positions. And so usually we rewrite this. You can rewrite it in front or on the 2, but it's mostly so that you don't lose it, right? So then I do arbitrary notches for my x as well. 1, 2. When x is 2, y is on this line here, 2, -2 over 3. I'm gonna rewrite this part here. Now I'll take the edge of my calculator, I guess. Use that as my straight edge. Oh, no. Yeah. I almost forgot. I have a snazzy ruler. Can you guys see that? Yeah, you can see the ruler. The ultimate straight edge. I wanna, if I can use it. Connect the 2 dots. And so draw the line. And extend it. How can I? There. The thing about lines is they keep going forever, right? And so often we'll put a little arrow on each end. You don't have to, but often we do just indicate that they keep going to -infinity, +infinity, right? Nice. Any questions so far? Okay.
So when we're trying to find the variables for each, just do 2 different sets of equations, like 2 different, substitute like in like a 2 for x and a 3 for x.
Yeah, because then you can solve for the y, the corresponding y coordinate, and then you'll have 2 points. Right. Nice. So we can do the same thing for these 2 here, but I do want to talk about these little guys, right? 2y = 3. What's that going to look like? Gonna add a page here. Sketch 2y = 3. We're just plugging in values of x and solving for y. But now I don't have an x, right? We could rewrite it if you want to. You don't have to, but if you want to, you could rewrite it like we did and say 2y plus 0x is equal to 3. We could use the same method that we were using, right? Then I can set up a table of sorts, pick 2 values of x, plug them in, solve for y. So I have 2y plus 0x is equal to 3 in general. So if I let x be, well, 0, my go-to, let's stick with that. Doesn't change anything. 2y plus 0 times 0 is equal to 3.
Oh, it'll just be an improper fraction in this case.
Uh-huh. So then we get 2y is equal to 3. So y is 3 over 2. What about when x is 1? 2y plus 0 times 1 is 3. Well, put you in the same spot, right? So it doesn't matter what x is, y is always going to be 3 over 2. I'll say for any value of x. So we could write these coordinates as well. 0, 3 over 2, 1, 3 over 2. We can apply the same technique. It's just kind of boring. Why? Because here, if I have x and I have y, if I let x be 0, I get a y of 3 over 2, which is 1.5, right? Which is easier to think about. Nice, clean decimal. And so let's see here. I'll put it at 1.5 here. I'll use my lines on my page, roughly. Okay. So when x is 0, y is 1.5, which is 3 over 2. When x is 1, let's put that here, y is still 1.5. X is 2, y is still 1.5. So now, if I try to draw it properly, close enough. They're all supposed to be on the same horizontal line at y equals 3 over 2. So if x doesn't matter, then you get this horizontal line, y equals 3 over 2, or at any value of y. And I personally had a hard time with horizontal and vertical, but it's going to come up a lot. And so then I think about, the horizon here, making it horizontal. Sun comes up or is setting, I don't know, over the horizon. And so this is a horizontal line. And like all the things so far, if you remember one of them, then you remember that the other one is the vertical line. All right. So what does a vertical line look like? Probably the same. It's just if we have a coefficient of 0 on the y instead of the x, right? Like this. X minus 2 equals 0. Sketch x minus 2 equals 0. could go through the same motions if you want to. Right? You could say, or x plus 0y is equal to 2. And add the 2 to both sides. But I think it's easier to just solve for x is equal to 2. Right? It doesn't care what y you give it, x will always just be 2. Right? So then, and you can confirm it with the table like we have been doing, but you can kind of just sketch it out. If x is equal to 1, 2, remember this is your x and this is your y. X is equal to 2 all the time for all values of y. And so I get a line, a vertical line. At x equals 2. You can give it any value of y, and it would still just give you x equals 2. Any questions about that? Yeah.
You know, if there's no questions that happen. Or yeah, the x equals 2, but it's a vertical line. Does it mean it's 0 and 2, 0?
So in this case, it depends. So it can take on any value of y. Let's say y is 1. Then at this point, x is 2 and y is 1. But here, if I move up to 2, then at this point, x is 2, y is 2. No matter what value of y you give it, x will always just be 2. Nice. Bring this up. We already sort of introduced the intercepts, okay? But the points where a line crosses the y-axis or the x-axis are going to be your intercepts. You're going to have x-intercepts and you're going to have y-intercepts. Okay? And if you think about the word intercept, right? Oh, it was intercepted, right? It was kind of jumped onto, right? And so then you can have x and y. The x is intercepted, right, on the x-axis. But what's happening at the x-axis, right? That's going to be whenever y is equal to 0, right? So this happens at y equals 0, the x-intercept. Let's pick a different color. The line intercepts, sort of, the x-axis when y is equal to 0. Right. The easier way to think about it is to find the value of the x-intercept, you're going to force y to be 0, right? But conceptually, it's really important to keep track of, okay, so the x-intercept is where it crosses the x-axis, and what happens, or what is the x-axis? Well, it's where y is 0. Right. Same thing for the y-intercept. I can't seem to match the colors, so I'll just use the same colors here. The y-intercept is at x equals 0. Right? So this happens if I force x to be 0, right, then I know where it crosses the y-axis. So then the line intercepts the y-axis when x is equal to 0. Nice. So usually those make kind of nice anchors for drawing your line. I was trying to avoid it, but they are the easiest way to draw a line. Right? And so we can use the x and y intercepts as the 2 points to draw a line. Let's grab one of those lines that we didn't use. How about, why not? 3x is equal to 4y minus 7. So what if we have to graph this little guy? You can rearrange them if you want. You don't have to. You can keep them like this. And we can use the same method that we were using, right? But now let's force x to be 0. And then for our second point, instead of forcing x to be something, we'll force y to be 0, right? And then we'll have those 2 points, right? X, if 3x is equal to 4y minus 7, let x be 0, then I get 3 times 0 is 4y minus 7. 3 times 0 is 0. Trying to find out how flexy we are. What if I just go I'm just gonna skip to the 3rd level and then we can rein it in. 4y is equal to 7. Skipped a couple moves, didn't I? Let's see. Maybe I backtrack. I want to get to there, but maybe, just maybe we're not there yet. It's really hard to tell.
Seven on both sides, or like 3 times 0 is 0, and so that's 0 equals 5. 4y minus 7, and then add 7 on both sides. So that's how you get the 4y over 7. But 7 over 4. Yeah, it's another improper fraction. I think it's like 3 point something, maybe. Oh, no,
4y. So 0 plus 7 Everyone's kind of hanging on. Then I do this often, okay? If you think about 0 plus 7, well, that's just 7, right? 7 is equal to 4y. 7 is equal to 4y, but I'm trying to solve for y. I always like to have whatever I'm solving for on the left-hand side. So I call it my revolving door, right? You can revolve things around the equal sign, right? And so then I just kind of swapped the equal sign. Instead of kind of thinking about things moving around, I just kind of moved everything around the equal sign, keeping everything the same, right? Because the equal sign has to keep everything the same. That's the whole point of it, right? Equality. And so now, eventually, right, if I can read the group, we'll just go from here to here, right? Seems reasonable. So then y is going to be 7 divided by 4.
It's actually 1.75.
7 divided by 4. Nice. I'm not rounding, so I can use a straight equal sign. But it is easier to think about 1.75 rather than 7 over 4. So too much fun in the hallway. Running? Are you kidding me? I don't think I've ever run down these halls. And I'm here late a lot, so I probably could. Okay. New Year's resolution. I'll run down these halls one night. Has to be at night, I guess. Okay. It's hard to put them on the same table. I'll move this over a little bit. If x is 0, this makes it the y-intercept, right? If I force y to be 0, same deal. 3x is equal to 4y minus 7. Just plug in y equals 0. 3x is equal to 4 times 0 minus 7. 0 minus 7 means x must be negative 7 over 3. Which I don't think makes anything nice. 3 is kind of a troublemaker in fractions. Oops. Mm. 2.33333. So I always tell my classes, so I did do my undergrad in math, of course, and not of course, but I did. And so the problem with that is everyone thinks I'm really good at like mental math. That's absolutely not what you do when you do a math degree. And so by the end of my undergrad, I caught myself doing 1 + 1 on my calculator just to make sure that I knew what I was doing. And so now I just refuse to do mental math. I always just use my calculator. I don't trust myself. But that's why that's okay. Don't have to. We really don't have to. You're not just gonna have a calculator in your pocket. Well, we do. I know, right? if y is 0, by definition, that makes this the x-intercept, right?
I got a question like this on the test. Would it just say find the y-intercept and the x-intercept?
I would probably keep it generic and say graph this, and you can do it however you want. But I would say probably that if I give you an equation like that, probably the easiest thing is to find the x-intercept and the y-intercept. Right? But choose your own adventure. Right?
So I'm just trying to figure out plot of the y-x-intercept. It's still got a right answer, and if you plotted the x one, you still got a right answer?
Hmm?
Okay.
Yippers. So now, I guess the hardest part would be taken care of because I would give you the grid. But the hardest part is figuring out where to put your axes and how much space you need. So let's see here. If I have x is 0, y is 1.75. So that's kind of my highest point of y. And if y is 0, I need to make room for at least x equals negative 2.333, which leads me to draw something maybe like this. If x is 0, y is 1.75. Kind of backwards. If x is negative 2.333, let's just kind of plunk it here-ish, then y is 0, putting me on the x-axis as promised. Any 2 points on the line will do. Take a straight edge. I'll see if I can find that snazzy ruler again. And then you're done. Craft a line. Okay. Nice. We'll warm up. Good. Any questions before we kick it up a notch? One notch. Oops, that's not what I wanted. I want this one. My pointer.
Besides the table, are there any other ways to find the x-intercept? I think for me the table is the easiest.
Yeah, I'd say the table is the easiest. I'm sure there, yeah, but I think the most common is the table. I can't think of any other reasonable ways to do it. Okay, so graphing a line from its equation in parametric form. Uh-oh, whatever that means, yeah. So sometimes we might have something like this, where x is going to depend on t, right? We usually say it's a function of t. We're not really at, functions yet, but it depends on t. So it takes some input t, and y also takes that same input t. Okay? And so t is called a parameter, or sometimes we call it a dummy variable, just kind of a variable that holds things together in my mind. Okay, and so what you can do is you can let t be multiple values and figure out what x is and what y is for each of those time points, presumably. Usually if we use t, they're for time points. Okay? But it works generically as well. So if you have a situation like this, right, both x and y are in terms of t. So we can say t, I can force t to be some numbers. And then I can solve, okay, I can figure out x is 3 plus 2t. For simplicity, let's just let t be 0, 1, 2. You could go crazy 1.5 or something like that, but let's not. 0, 100, 500. Why not? Let loose. But the numbers would be kind of big. And I don't want to draw big numbers like that. Yeah. So if t is 0, x is going to be 3 plus 0. So then x is going to be 3. At the same time, y is 1 plus t. Right. So they depend on t in different ways. So 1 plus 0, so then y is equal to 1. Giving us one final coordinate at t equals 0, x, y is at 3, 1, right? T equals 0 is now kind of shoved in the background, right? And the xy coordinate is just 3, 1, and that's the one that you're going to draw. Right? Let's do t equals 1. So then x is 3 plus 2 times 1. So x is 5. Then y must be 1 plus 1. I should just write 2. Speaking of 1 plus 1.
Just out of curiosity, you probably use the dummy variable outside of graphing too, right?
Yeah,
All you need is 1 or 2 variables and find an answer or.
Yeah, totally. Yeah, so you could, for example, you could solve for t, set them equal to each other, right? That kind of thing. We use dummy variables in statistics a lot, kind of placeholders. And so for graphing, yeah, I don't really see, it's good to have seen it, right? That we can have kind of more involved ways of representing a line, but it's not very common. Yeah.
So for the dummy variable, we're going to be given it within the equation, or can you just add it?
So here it would be given like this,
Yeah.
right? Like
Yeah.
I would kind of give you t, and I would say t is a dummy variable.
So you couldn't just add it to the equation.
Not in that sense. You might have, I'm trying to think of a scenario where it would make sense to have one, right? But probably time points, right, would be a case where x depends on time and y depends on time, but in a different way, right? But yeah, nothing's coming to mind, but so yes and no. How's that for an answer? Good measure. Let's do t equals 2, 3 plus 4 must be 7. You want to be careful only because I see it a lot. Right here, when we have x is 3 plus 2 times 2, BEDMAS says you have to do the multiplication first, right? And so you have to do the 2 times 2 first, and then you can add it to the 3, right? Otherwise, if you did 3 plus 2 and then times 2, you'd get to the wrong answer. There'd be illegal math. You don't want me writing illegal math on your test. That's bad. Okay. And hey, why isn't it? Listen to me. 1 plus 2 is 3. So 7, 3. Looking at these numbers, I need to make room for x equals 3, 5, and 7. Right? So I need quite a bit of room on my positive x-axis. And then my y's, I need to make room for 1, 2, 3 at least. Right? And so I don't need a ton of space on my y-axis, but I do need quite a bit of room. Did I do it? No, I need maybe one more. Just sketching it anyways, but you know what? Let's go crazy. Like I said, it is virtual space. I have to remind myself. So I can have x is 1, x is 2, x is 3, or sorry, y. Ugh. 1, 2, 3, 4, 5, 6, 7, 8. Good enough. When x is 3, y is 1. When x is 5, y is 2. When x is 7, y is 3. Looks like they're on a straight line, which is good. I wouldn't be surprised if they weren't exactly on the line. Why? Well, because I did my scale pretty roughly, right? And so I'm not really expecting them to be that good, but not bad. If I do say so myself. I'll pretend that this one was more like here. Just make a bigger dot. So then you can have that dummy variable link, but you still end up at a line. All right. You could eliminate the t. What could you do? We could have eliminated the t, right? The dummy variable. Oops, this is we had x equals 3 plus 2t, and we had y equals 1 plus t. Couple of ways you could do it. If you wanted to kind of get rid of this middleman t, right? Mr. T. And so one of the things you could do is you could, oops, not the ruler. I want the pointer. is here, you could solve for t and then take that t and plug it in here. Right? So now what you could do is you could solve for t, which would look like this, y equals 1 plus t. So t is y minus 1. Which is true, right? We saw up here, if y is 1, t is 0. If y is 2, t is 1. If y is 3, t is 2, right? Y minus 1. So that's still true. Then what could you do? And then we could substitute t equals y minus 1 into x equal 3 plus 2t. Which means that x is 3 plus 2 times y minus 1. If you expand that, 2, we can expand and simplify, right? So then I could get x is 3 plus 2y minus 2. Can simplify a little bit more. Maybe I'll do this. I know, kind of sneaky, but I just need one more line. Just one more line. Three minus 2 can simplify just to be 1. And we can say that x is 2y plus 1. Or 1 plus 2y if you prefer. But they're the same. Now all of a sudden we're back to something that looks exactly like what we were working with. So you could use that instead if you prefer. Nice. Questions about that? We've already talked about horizontal and vertical lines. I couldn't wait. Yeah.
Oh, can I go to the bathroom?
But if you have a line that has the form x equals a, where a is some constant, then you have a vertical line that passes through a0. So we already talked about if you have a line at x equals a, right? That makes a vertical line, and versus this horizontal line at y equals b. But like I said, we talked about horizontal and vertical lines and their behaviors. We're about to talk about their slopes, but I'm trying to not get ahead of myself. See if I can move all this up. I can. Score. How about the slope? Rise over run. Might be ingrained, might not be. All right. graphically, what does the rise over run look like in terms of points? Right, and so the slope, oops. The slope of a line is usually denoted by a lowercase m. In the case of y equals mx plus b, right? And so the slope is rise over run, right? If I just give you an arbitrary line like this, how are you going to find the rise? You can pick any 2 points on this line, right? And let's let this point be x1, y1, and let this point be x2, y2, right? Point number 1, point number 2. Arbitrary points. Then, let's change this to light blue. This distance here is the rise. Using these points, the easiest way to find that distance is going to be taking y2 minus y1, right? Taking this change in the y's I will say anything in these green boxes, I'll put on your formula sheet, right? Or I would put on your formula sheet. Can't remember where we landed on that. It's not really go time yet, but if I'm making your formula sheet, I would put it on your formula sheet. But also if you're making your formula sheet, you should probably put it on your formula sheet, right? Unless it's up here. So here, the green means it's definitely going to be on your formula sheet. I think finding the rise, right, that distance is kind of intuitive. You want to find the distance between y1 and y2. And the way I drew it, it's kind of obvious that y2 is going to be bigger than y1. And so if I want to find that distance, subtracting the two kind of makes sense. I guess you can use the same kind of argument for the run. Maybe I should change colors here. Right, x2 is still bigger than x1, right? But for some reason, I don't know, it's not as obvious to me that it should be x2 minus x1. I just take it and run with it, obviously, right? The thing is, as long as you're consistent about this is your point 1 and this is your point 2, it doesn't matter. You could have let this be point 1 and this be point 2. Doesn't matter. It doesn't change anything, right? As long as you're consistent. So from this becomes the rise. Can't seem to keep my colors the way I want them to be. y2 minus y1 over x2 minus x1, which is what's on your formula sheet. Is that right? I've been blabbing that long. I can really blab. Here, you're given 2 points. So we can graph the line, right? 2 points is all we need to graph the line. But, so let's start with that. But then we're also asked to find the slope. Right? You can use the slope just visually looking at the rise over run. That's totally fine. Which is why I would probably graph it first. Or using the formula. I like to just plug and chug with the formula, but maybe as we're warming up to this stuff, doing both might be good. So we have 2 points. X is -2, y is 3, and x is 4, y is -1. So in terms of kind of figuring out how to allocate my graph, right, I need to make room for at least x equals -2 to +4, right? And my y's, I have to make room from +3 to -1 at least, right? And so let's do something like this ish. 1, 2, 3, 4, -1, -2. 1. Uh-oh. Forgot about my y's. No worries. Power of the virtual paper. There was a time when I would do all this on a document camera. Costly mistake. Hey, no. I'm ready to fall asleep. Just to 3. That's all I need. And to -1. Just looking at my x's. Keep them straight. Doesn't matter which one you make 0.1 and which one you make 0.2, but let's make this x1, y1. And let's make this x2, y2. If x is -2, then y is +3. If I have to draw that point here, that'll be here. And if x is +4, y is -1, which puts me somewhere down here for -1. I can connect these. So we've graphed the line just using the 2 points. If you wanted to, could have found the slope and used the slope to draw it, but I find that that's more complicated. I think it might be nicer to graph it first, and then if you prefer to use the line or the graph to find the slope, then that's totally fine. But right, you want the rise over run, that's the slope. But let's practice using formula y2 minus y1 over x2 minus x1. I've assigned y2 to be -1 and I assigned y1 to be 3. But like I said, as long as you're consistent with which one's 0.1 and 0.2, it doesn't matter. So then the slope is -1 minus 3 divided by 4 minus -2. Being careful with that -2. I like to throw in some brackets around the -2 just so you remember to do what? Turn that minus -2 into plus, right? So then I get m is -1 minus 3 a rise of -4, which makes sense, right? It went down 4 units, right? It went from +3 down to -1. Right? So it went down 4 units divided by 4 plus 2, which is 6. I'm fine if you just leave it like that, or if you want, well, my calculator just simplifies it to -2/3, right? But I'm not expecting you to simplify it. You're allowed to. If your calculator does that for you, then go for it. But I'm not expecting it, okay? Or if you prefer, or -2/3, but I'll put that in brackets, right? Or -0.666, repeating. Let's make this 7 instead. Why not? Usually we're doing calculations with the slope, so you don't want to have to lug around too many decimal places, but unless you're working with money, then it's important. You want to keep all your decimal places. Okay. The other 2 examples I have are the same. We're just doing the same thing. Maybe or I shouldn't do that, but maybe I'll leave these and you can try them on your own. And before I post the notes, I'll post the solutions. Right. I'll add those in.
Wait, sorry, was the answer on the previous one 4/6?
-4/6.
Oh,
Because -1 minus 3 is where the negative came from. Let me just scroll ahead, blah, 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 blah. Okay. Could do reverse, right? So if we have to graph a line that passes through the point 1, 2, and it has a slope of -3/4, then first thing that we don't know yet, but I'm about to tell you, is that just in general, if you have a negative slope, right, then a negative slope has this downward behavior, right? So a negative slope is going to look something like this. It's always good to have an idea of what you're expecting it to look like, right? Whereas if you have a positive slope, so versus a positive slope, is going to go up like this, or kind of some version of that. I always find that it helps if you imagine a little arrow at the end of it. If you start at the left and then you end at the right, then the positive slope is of course going up and the negative slope is going down. So my first clue here is that I'm expecting a negative relationship, right? And so what I can do is I can plot this point. Let's plot if x is 1, y is 2, 1, 2. And if the rise is -3, right, then I have a decrease of 3, right? And so, oops, let's go here. I want to go down 3 units, putting me at -1. And then I want to move to the right 4 units. Putting me at not 1, but 5. Which makes this 5, -1. You can confirm by calculating the slope and making sure that you get to the same spot. Wait. Oh, why is it so hard this time? But there we did it. Didn't do a very good line, but that's okay.
How did you find the 5?
Because so I had to move down 3 units. Right, the rise was -3, which means just moving down 3 units. And then I had to, the run was +4. And so I started at x = 1 and I moved over +4 to put me at 5.
How did you get this down?
From the original point here. I started at 1, 2. And so here, this line follows at x = 1. And then I moved over 4 units. Nice. How about I skip to the good stuff? If we are able to rewrite the equation in the form y = mx plus b, to rewrite the equation in the form y = mx plus b, right? M will be the slope. M will be the slope, whatever is attached to the x, right? The value attached to x is the slope. So you're gonna have m attached to x. You've solved for y on its own, right? So in this scenario, y is on its own and b is also just a constant, right? Knowing that, how would you find the slope of the line? 2x plus 3y is equal to 6. I personally would rearrange it into the y = mx plus b. We haven't introduced it yet officially, but I'm getting kind of impatient and also running out of time. So, right, I think the easiest thing to do is to rearrange it and just solve for y and see what happens. So if we get from 2x plus 3y is equal to 6, and I'm trying to solve for y, then I get 3y is 6 minus 2x. Right? I'm trying to get y on its own, but in order to do that, I have to move the 2x over to the right-hand side. And then the last thing I need to do is I need to divide both sides by 3. So I get y is 6 minus 2x divided by 3. It's really tempting, but also illegal math if you just cancel this 6 with this 3, right? Because this -2 is also being divided by 3. To emphasize that, usually what I do is I'll split this fraction up, right? And so here, you can rewrite this as y equals 6 divided by 3 minus 2 over 3 times x. Right? Then you have legal math. Right? Now, if you simplify the 6 divided by 3 into 2, that's fine, that's safe, right? But you have to have the -2 over 3 still. And so I get y is 2 minus 2 over 3 times x, which is now kind of sort of ish. It's in the y equals b plus mx form, close enough. Whatever's attached to the x is the slope. -2 over 3. Which also tells me that this relationship, if I was to draw it, should look something like this, right? It's negative.
So the 2 and the x just kind of hang out.
Yeah. Yeah. So this x is just ready to take on any x and return what the value of y would be on the line. And the 2, spoiler alert, is the y-intercept. When x is 0, y is 2. Nice. But I think we'll save that for next week, I guess. I don't get to see you again till Tuesday. Maybe I'll clear this all up. A little bit of luck. If you have any questions, let me know. But otherwise, we'll just keep working through chapter 1 on Tuesday. I hope you have a great weekend. We'll stop this.